In this video, we show how we apply sequential linear quadratic control in a model predictive control fashion to two different robots, a ball balancing robot and a hexacopter. Let's first take a look at disturbance rejection performance. The ball bot is given the task to stay in place. When disturbed, the MPC controller reacts compliantly and plans a return trajectory to the initial position. This behavior cannot be achieved with a static feedback controller. In this example, we see how a standard LQR controller significantly overshoots when disturbed and finally becomes unstable. We also disturb the hex rotor while it is trying to reach the goal point. Here we tuned the MPC controller for accurate tracking, aggressively rejecting disturbances. While a regular tracking controller would force the hexacopter onto its original path, the MPC controller designs a new trajectory to the goal. In the second test, we evaluate how dynamic the controller can replan. In the case of the ball bot, we change its goal position with a joypad while disturbing the robot. We observe that the robot is still compliant. However, it also follows the given goal position by continually optimizing its trajectory. To test the replanning capabilities of the SLQ MPC on the hex rotor, we give it the task to always reach a goal position at the end of the room. To make the task more challenging, we randomly give it intermediate waypoints to fly through prior to reaching its goal. These waypoints are full state waypoints. To illustrate this, we add a positive forward velocity to the waypoints, forcing the hex rotor to pass them in forward flight. As a result, when being behind a waypoint, the hexacopter first has to fly back in front of the waypoint before passing it. Quick changes of waypoints pose no difficulties for the hex rotor. As a final test, we look at more dynamic motions of the hexacopter. In this scenario, the hex rotor has to pass through one of two windows to reach a goal point. The right window is too narrow to pass through horizontally, but it requires the hex rotor to pass through with a rolled angle of 30 degrees. Since such a pose is not statically stable, the hexacopter has to plan a dynamic trajectory to not collide with the window. Furthermore, we emulate a high-level planner which randomly switches the desired window to pass through. As shown, the hex rotor reacts to simple replanning requests with ease, finding non-trivial trajectories for the approach and pass-through. Since SLQ MPC optimizes trajectories over long time horizons, the resultant trajectories also consider the slowdown towards the target and passing the window. The MPC controller is active during the entire recorded sequence, including takeoff, window passing, and return. Let's look at one replanning in detail. First, the hex rotor plans to pass through the left window. Then, when requested to pass through the right window, the MPC controller optimizes a new trajectory in less than 17 milliseconds. Here we see snapshots of the hexacopter when passing through the right window, underlining the repeatability. Let's take a look at the evolution of the gains over one trajectory. In hovering phases or phases of straight flight, the gains are low. During agile maneuvers or when passing through the window, accurate tracking is required. Therefore, the algorithm increases the gains in these moments.